Okay, in the last video you saw that you can find the binding energy per nucleon of a nucleus like iron by finding the mass defect. So you take the mass of the nucleus and you subtract the mass of the separated protons and neutrons, and you get the mass defect like this. And 1U is 931.5 mega electron volts. And then if we divide by the number of nucleons, 56 in this case, you get the binding energy per nucleon. Okay, if we do this for different nuclei, we can plot a graph of binding energy per nucleon against mass number for those different nuclei. And we get some data that looks like this, and the curve corresponding to that looks like this. Okay, we've got a maximum here at around a mass number of 50, and this maximum has a binding energy per nucleon between around 8.5 mega electron volts. This is where the iron nucleus is. So the iron nucleus has the highest binding energy per nucleon, which means that it's the most stable nucleus compared to all other elements. Okay, so we have small nuclei on one end with very low binding energy per nucleon. And what they do is they undergo fusion. They join together with other small nuclei to make a larger nuclei. So this will increase their binding energy per nucleon. So all the elements in this region tend to do fusion. Okay, so with small nuclei, they undergo nuclear fusion, which is a joining of two small nuclei to make a larger nucleus, which has a higher binding energy per nucleon, which is more stable, up to iron. Okay, and all the ones on the other end, which are very large nuclei, they actually split into smaller nuclei, so roughly equal sized daughter nuclei. So this region over here with large nuclei, all the elements there undergo nuclear fission, which is the splitting up of a large nucleus into two smaller nuclei. Okay, in this example we have two hydrogen nuclei which can fuse to make helium-4 nucleus. Uranium-235 can be induced to split into two roughly equally sized nuclei. Show that 1 kilogram of hydrogen will release more energy than 1 kilogram of uranium. Okay, so if we take the fusion process, okay, it's got two hydrogens fusing together. So in this case, you can see there's a big change in binding energy per nucleon. Okay, so the binding energy of hydrogen is around 1.2 mega electron volts, and that's per nucleon. So I'm going to have to try and multiply that by the number of nucleon in each hydrogen, which is 2, because there's a proton and neutron. But then there's 2 hydrogens required for every fusion process, so I'm going to have to multiply that by 2 again. So that's the total binding energy of the hydrogen on the left hand side there. And on the helium, so helium has a much higher binding energy per nucleon, around 7.1 mega electron volts, and there are 4 nucleons, so that we need to multiply because that's the binding energy per nucleon. That gives me a total binding energy of 28.4 mega electron volts. So in the fusion reaction, per reaction is going to be 23.6 mega electron volts of energy released. While nuclear fusion, we're going to have the uranium splitting up into two roughly equal daughter nuclei. So uranium-235, that's got a binding energy of around 7.6 mega electron volts per nucleon. So multiply by 235 because that's how many nucleons there are. That gives me a total binding energy for uranium of 1786. Okay, and the two daughter nuclei, they have roughly 8.6 each. So multiply by the number of nucleon, and you have to add twice because there's two daughter nuclei there. Add that together, and you find the difference. You get 235 mega electron volts being released per reaction. However, it looks like the fission reaction does release more energy per reaction. However, we're interested in which one, 1 kilogram of hydrogen or 1 kilogram uranium. And as you know, hydrogen is much lighter. Okay, so each hydrogen atom is much lighter. So there's going to be more hydrogen inside 1 kilogram. Okay, I can use these equations here for moles, molar mass, and Avogadro's constant here to find how many particles there are in 1 kilogram of hydrogen and 1 kilogram of uranium-235. So this number here, the 2, is the molar mass of hydrogen, and 235 is the molar mass of uranium-235. And we've got 1 kilogram. So if we take the 1 kilogram divided by the molar mass, so remember that's in grams per mole here. Okay, so I need to divide that by 1,000, which is why I get 0.02 kilograms. So that gives me 500 moles, and each mole has the Avogadro's constant number of particles. So the total number of hydrogen inside 1 kilogram is 3.011 times 10 to the 26. However, we need 2 hydrogens for every fusion reaction, so we're going to have to divide that by 2. So the total number of fusion reactions possible is 1.506 times 10 to the 26. Okay, now with the uranium, so 1 kilogram divided by the molar mass, 0.235, so that's only 4.3 moles. and inside 4.3 volts multiplied by Avogadro's constant to get the total number of uranium atoms, and each one of those uranium atoms is going to lead to a nuclear fission reaction, because that will split into daughter nuclei. So we can see there are around, you can have, for every reaction of the fission, you can get 558.1 more fusion reactions occurring. Okay, going back to the energy release per reaction, we know that for every one fission reaction, we're going to have 58.1 fusion reactions. So that means the energy there is 13272 per fission reaction. And if we compare it to the energy released in each fission reaction, we get around roughly 5.8 times more energy being released from 1 kilogram of hydrogen compared to 1 kilogram of uranium.